And we're back. Welcome back. We skipped Tuesday's lecture. This is Thursday, the 16th of April, 2020. So today we're going to start Chapter 6 material pertaining to the link layer and local area network. And what we're going to do is understand the principle behind the network layer services. And in particular, we're going to talk about switches, local area networks. We're going to talk about VLANs. We're going to talk about data centers. And we're ultimately going to end in a day in the life of an internet connection. Okay, so let's take a look at some terminology. Hosts and routers in the network, regardless of whether they are wireless or an enterprise network or a home type network setup, hosts and routers are represented as nodes on the network, and there are communication channels, i.e. your links, that are pathways, and these communication channels can be wired, can be wireless, can be fiber optic, can be hybrid fiber coax, it can be copper wire twisted pair. And we have this layer 2 device, and in layer 2, the unit of transfer for packets is called a frame. And inside of this frame at layer 2 is the datagram that comes from the layer 3, which is, of course, routing and IP for the 5-layer internet stack. And so the link layer has responsibility of getting that datagram from one node in a network to a physically adjacent node over a link, regardless of whether that link is wired or wireless, copper, hybrid fiber, coax, or what have you, or fiber optic strand. And so the link layer's responsibility is to get that unit of transfer, the frame, in which the datagram is stored as payload information, and its responsibility is to transmit or get that unit of transfer, the frame, between nodes, one source and one destination, that share an edge or share a link. Okay, so that's what the link layer is purposed with, or that's its responsibility. And so this datagram is transferred using a number of different protocols because there are a number of different link types. For example, on the first hop for a link, you might use Ethernet. Now, Ethernet is what you'd use over a copper wire twisted pair. Over a wireless link, there's a wireless version of the Ethernet protocol, and you know that it's 802.11. 802.11 is the standard number maintained by IEEE, the Institute for Electrical and Electronic Engineers, for that wireless Ethernet protocol. And so all 802.11 B, C, and is different versions of this 802.11 protocol, and they're all different protocols for link layer, this transfer between nodes that are connected directly in wireless broadcast radius. Okay, so each link layer protocol provides a set of services, and these services are purposed with getting that frame from one node over that link to another node, be that node a host or a router. And in the book, they like to use a lot of human analogies. For the link layer, they use the analogy of transportation. Let's say you're going from Princeton, New Jersey to Lausanne, Switzerland, and you might take your limousine to get you from Princeton, New York to JFK Airport in New York. And then you might take a plane to get from JFK, from New York, over that long hop to Geneva, Switzerland. And then once you're in Geneva, Switzerland, you might take a train to get from Geneva to Lausanne. And so in this analogy, the person traveling, the tourist, would serve the role of the datagram, and the transportation segment would serve the role of communication link, and the transportation mode is your link layer protocol. It's how you're going to get across that link. The travel agent is your routing algorithm. It determines what set of links that you should traverse. So in this particular case, you have one link that's to get from your local airport, Princeton, to get to JFK Airport. So that would be one hop. And of course, there's a protocol that you use to get there, and that transportation mode, the limo, is the way you get the tourist from Princeton across this link to JFK. Then for the next hop would be from JFK Airport to Geneva, Switzerland. That's an airplane, air travel. And this air travel is responsible for getting that tourist from JFK to Geneva, and that's a different methodology for how you do the transfer. And then likewise, once you're at Geneva, there's yet another hop that gets the tourist from Geneva to Lausanne, and how you ride the train, that train operates differently. It's a different means of transfer. And so this analogy in the book talks about the fact that when you have a route between two end-to-end communicating endpoints, you're going to traverse a number of links, and each link layer service between two communicating endpoints can use a different protocol to get that segment, that frame, from one link, along one link, to the other link. So you can have different link layer protocols for each link that is traversed by this datagram, this frame. Okay, so what does a link layer do? It's responsible for so-called framing, and framing is the putting of the datagram into the frame. And so let's remember, you have the 5-layer internet stack. You have your application layer. You have your transport layer. We talked about that. You have your network layer. And that network layer deals with datagrams. And we talked about Internet Protocol IP. And so this datagram below the network layer is the link layer. And below this link layer is the physical layer. And so this framing is the taking of this datagram. So you have your datagram. And what the link layer does, it takes this datagram that it gets from the network layer above, and then it encapsulates it, wraps it into a frame. So that's a frame. And that frame includes some header information, LH, link layer header. And so this idea called framing is the putting of the datagram as payload in that link layer in a packet maintained by the link layer, constructed by the link layer, and it adds to that frame header information that's meaningful to other link layers that are directly connected neighbors to this particular node on the network. So then the other thing it does is this link access. This link has access to the physical medium, and that physical medium is what takes this bit information and translates that into signal information. It could be electricity over a wire, it could be radio frequency information if it's wireless, or it could be pulses of light if it's fiber optic strand. Okay, and so the link layer does the framing, the encapsulation of the datagram, and the addition of header information that controls the behavior of the other link layers on the network with which it communicates. And then there's the link access, that is the interfacing with the physical layer. And so this channel, this physical layer, there are multiple link layers that are going to be accessing it. So here is a link layer, here's a physical layer of another node. Here's a link layer. And so these other link layers and physical layers are going to be accessing the same channel. And so sometimes this channel is shared. In the case of wireless, they're all trying to access the wireless airways at the same time. Sometimes it sort of arbitrates between these, but nonetheless, this channel is shared, and they have to kind of mitigate who's going to access at one time, because if they're shared, you don't want all these conversations happening at the same time because you get interference. Okay, and so you also have something called a media access control. Media access control address. And this media access control address is used to identify the unique link layer associated with a particular node. And more correctly, this is going to be a unique network interface card, and we'll talk about that in a few slides. And so it's so-called media access control address because this is a shared medium for your link. You need to uniquely identify, okay, is it this link layer or is it this link layer for node A versus node B that I'm referring to? And so this media access control, or MAC address, it's very different from the IP address. The IP address identifies the network layer and it's associated with the interface card, but the MAC address uniquely identifies that network interface card on the shared medium, on the local network, and this link layer address is unique. Okay, so what does this link layer do? It provides reliable delivery between so-called adjacent nodes. let's say if you have host A here, and host A is connected to another host through something called a link layer switch, host B, and let's say host B is also connected to a router through that switch. Now, these adjacent nodes, this switch, from the perspective of the link layer, it looks like it's just a single connector, right? To nodes A, B, and C, they believe or think that the network looks like the following. Here's the router, and here's A, B, and here's X. That switch is a pass-through that acts like there's just a single conductor, and we'll talk about that in great detail as well when the time is appropriate. And so here we have adjacent nodes. A is adjacent to B, A is adjacent to the router, B is adjacent to the router, B is adjacent to A. And so what this link layer provides is reliable delivery between nodes that share the same network or share the same shared medium. And so this RDT that we talked about when we talked about the transport layer, it's a similar thing that happens in the link layer, but we just won't repeat that. Just assume that it's the same. And you can certainly look this up, but that's beyond the scope of this class for the link layer. Okay. And so this reliable delivery is typically not used on certain media that have low interference, low noise. So on a fiber optic cable, you're not going to have very much RDT types of mechanisms, timers and retries, acts. You're not going to have much of that implemented because fiber is very reliable. You're not going to have too much disturbances, and therefore you're not going to have too many acts or too much corruption happening. But for media like wireless, where you have a lot of interference, you're going to have a lot of RDT types of protocol aspects and features implemented. And so wireless has a higher error rate, and therefore you tend to have a lot more of the RDT types of mechanisms implemented, like corruption detection of bit errors and things like acknowledgments and retries and timers and things like that. Okay, retransmissions. And so we also have flow control in link layer services, and we talked about that with the transport layer. We won't repeat that. Error detection, and errors are caused in wireless by so-called signal attenuation. The further this signal propagates in the airwaves, the weaker it gets over time. And so if you want to communicate over long distances, you need high frequency and high energy, high power wireless signals. And so you can detect these errors. You can also correct these errors, and we won't talk too much about that. And there are different types of link layers. Some will communicate half duplex, meaning that you can communicate bidirectionally, but only one direction at a time, or full duplex, meaning that you can transmit and receive, send in both directions between sender and receiver at the same time. So there are lots and lots of different variations of link layer services, but at the end of the day, the link layer is responsible for getting data between two nodes that share the same physical link or physical medium. Okay, so where exactly does this thing exist? Well, the link layer is implemented. There are a bunch of different variations for how it's implemented, but for the most part, it's implemented in a network interface card. Now, this network interface card looks like this. It plugs into your PC bus, and on that interface card is a bunch of chips that implement all these features like framing and physical access, media access, and the error correction and RDT and all that good stuff. Now, another implementation for these is to have a chipset, right? So right on the CPU board, you have a bunch of chips that are soldered on, and these chips implement what would otherwise be on this interface card. And so here we have a diagram, and this is your von Neumann architecture. You have your CPU, you have your memory, you have your network controller card, and they're all interconnected by a high-speed bus. And this is a typical PC, whether it's a laptop, desktop, so forth. And so this network interface card consists of a controller that guides the logic. It's sort of a silicon version of an algorithm someone's implemented that implements your RDT and all your other link layer services, and it connects through a converter, A to D, D to A, analog to digital, digital to analog converter, that knows how to create the right type of energy signal energy, be that pulses of laser for fiber optic strand or frequencies of electricity, sinusoids if it's copper wire, or radio frequency signals driving an antenna. It knows how to convert this binary information into physical signal information, okay? Both on the outbound side as well as the reverse on the inbound side. And so sometimes this will be in hardware. Sometimes it'll be a combination of hardware and software. Sometimes it'll be hardware and firmware. Firmware is a hardware version, if you will, low-level hardware version of software. It's reprogrammable. And so you have many different ways in which your link layer can be implemented. And certainly the more expensive one, and therefore the fastest one also, is purely in hardware. Okay. So we have in the CPU running the application layer, transport layer, network layer, and the software side of the link layer. And then we have in the network controller or the network interface card, we have the hardware side of the link layer and also the physical interface. Now, we don't spend any time in this class, or at least not too much, talking about the physical layer, except to tell you that they exist. You could spend a whole graduate degree just on dealing with this physical layer and how you manipulate signals to get your data across the physical layer reliably and over great distances. Okay, so what happens? You have these network adapters. They communicate. They get a datagram from the network layer, which is in the CPU, and this datagram comes into the controller. It's encapsulated here in a frame. This is a frame, and this frame has as its payload information the datagram associated with the network layer. Now, of course, there's some other header information that's meaningful to the link layers. And so the sending host puts this frame on the shared medium. It gets transmitted across. It's picked up by the physical layer of this controller on the receiver, and then it decodes that information, converts it from signal energy back to bits and bytes, and then extracts the datagram and sends that datagram up to the network layer, which is running in the CPU, that runtime. Okay, so the sending side encapsulates the datagram into a frame and adds other header information. This header information includes error checking, flow control information, etc. And then the receiving side, it looks for the errors. It looks checks for checksums and things like that. It extracts the datagram, passes it to the network layer, which is the layer above on the receiver side. So let's take a look at access to the physical medium. Now, there are two types of links that you can have. One is point-to-point, and this is sort of more historical, used in dial-up, where you'd have a telephone that would connect using dial-up for your network access using telephone wires, and you go between your telephone connection for ISDN lines going to the switch for in the central office of the phone company. And so that's kind of more historical, but there's also broadcast-based medium, and these can be a shared medium or a shared wire. And you have old-fashioned version of Ethernet, which did not use switches. We'll talk about switches. It was a wire-based broadcast medium, and all of the communicating nodes would tap into the same physical medium, be that coaxial cable or twisted pair Ethernet. Then you also have upstream hybrid fiber coax. That is also a broadcast medium. And then you also have wireless LAN. That is also a broadcast medium. And so here in this picture here on the left, we have a shared wire. This is your Ethernet or your coaxial cable, physical copper-based conductor. And then you also have shared wireless here using radio frequency. This is your 802.11 Wi-Fi. Satellite communication, satellite-based internet. Satellite-based internet is very popular for people in far-flung parts of the country where you don't have the infrastructure for the telephone wires or the fiber optics running. And that is a shared radio frequency, but it's different frequencies that can travel much further into space and bounce back down to other parts of the Earth. Now, when you have this broadcast shared medium, it's almost like people at a party, right? Everyone's talking at the same time, and everyone can hear the conversation of others. And if two people want to communicate, let's say this gentleman wants to communicate with this gentleman, if they're all talking, what ends up happening is nobody can hear one another. So in order for these two to communicate, this person to talk, and this person to get that communication, this person to respond back with some response, that means everybody has to be quiet except for those two communicating endpoints. Now, in order for everyone to be quiet, they have to understand when others are broadcasting on this medium. And so there are methods for arbitrating the access to a shared medium so that only the two communicating endpoints will be talking at the same time. Now, sometimes you get two people trying to talk at the same time who shouldn't be talking at that point in time, and that's called a collision. And what a collision means from a computer standpoint, this wireless shared RF, that means you have a lot more energy in the airwaves. And so each one of these has an antenna. If you are wireless, let's say this person were a laptop had a wireless, if more than two people are talking, what's going to happen? You have more radio frequency energy in the environment, and therefore they're going to pick up that energy, and the energy levels they detect are going to be higher, which means more than one other person is talking. Okay, so these are broadcast media. Let's take a look at the addressing, how you uniquely identify these media access cards or these Ethernet cards. They're in IP in the network layer. We talked about the 32-bit IP address. It was a dotted quad, and this was a unique address for the network card. It allowed the router to identify some destination endpoint for the network layer, layer 3. And it was used for the forwarding decision, whether it was traditional routing, control plane, the result of traditional routing, or the result of SDN style routing. Now, this media access control, i.e., the physical Ethernet card, the LAN card, has its own address called the media access control address, or the MAC address. Now, the purpose of this address, and this is very different from the IP address, is it identifies that Ethernet card or network card locally on the local network. And moreover, this MAC address is unique for every single Ethernet card. Let's take a look at that. The MAC address is 48 bits, and it's arranged as two 24-bit segments. So you have 24 bits, and then you have the other segment of 24 bits. Now, of course, the first 24 bits, uppermost, that's used to uniquely identify the manufacturer or the vendor. And so if you're Apple, you have a certain 24-bit number that only Apple can use when they make network cards. If you're Toshiba or Intel or whomever, you have a specific vendor ID. And so the other 24 bits uniquely identifies the network card. Now, of course, Apple network cards are going to have a different 24-bit uppermost bits than Hewlett-Packard network cards. And so these are unique, and they should be unique, and they are unique on every card. Now, of course, certainly, if a particular MAC address, let's say, for this network card, you only have 2 to the 24 different network cards a particular vendor can make. Now, if you ship one to, say, Germany and the other to Hawaii, it's very unlikely that those two network cards, if they have the same exact address from the same vendor, that they're going to be on the same network. So you can kind of mitigate that. But for all intents and purposes for this class, the MAC addresses are absolutely unique one-to-one. There's no repetition because they're on the same network. Okay, to be repetition, it's very unlikely that's going to happen. So they're all unique. These MAC addresses uniquely identifies the link layer of that particular network card. And so this MAC address is used locally on the same shared medium, the same network, the same local area network, to get one frame from one interface to another physically connected interface. And that physically connected is very, very important. And so this MAC address, it does not identify MAC addresses that are on another network. The router's not involved here. It's only on the same physically connected interface. That means interfaces that share the same network, be that wired, be it fiber, be it wireless, and so forth. Okay, so this MAC address is 48 bits, as we said. It's two 24-bit segments. And this MAC address, when you read it off, it exists as a number of hexadecimal digits. So one hex digit represents base 16. And as base 16, it's a number that can go from 0 to 15. Now, 0 is 0, and it goes through 9. And once you hit the number 9, for the number 10, you say A. For 11, you say B. 12, you say C. 13, you say D. 14, you say E. And 15, you say F. So one so-called hexadecimal or base hexadecimal or base 16-digit is represented as a 4-bit number in binary. And so if you have 4 bits per hex digit, that's 1, 2, 3, 4, 5, 6 hex digits. 6 times 4 is 24 bits. And so the first 24 bits is represented as 6 hexadecimal numbers, and that's going to be the vendor identification. And then this is going to be the unique card number. And remember, these MAC addresses exist on a network basis. Okay? All right. So here is an example MAC address, and that's also why when you see Wireshark, it knows that your network card, the MAC address, if you expand the link layer portion of Wireshark, that it says Apple or Hewlett Packard. It knows what the vendor is because those unique vendor portions of the MAC address are known. Okay. And if you are a new vendor and you want to start making network cards, well, you have to go register for a vendor ID. And you can just start stamping out whatever number you want for the card number, but you have to use this vendor number for the uppermost 24 bits of the MAC address. Okay. So each adapter on the local area network has a unique LAN address. So here we have a single network, and we have all of these nodes, 1, 2, 3, 4, on the same wired or wireless local area network. And you notice their MAC addresses, they're all 48 bits, and you'll notice they're unique. Now, in this diagram, this green symbol, that's the network adapter, and we've decorated it with the MAC address associated with each network adapter. Okay, and so these LAN addresses are unique, and if you have a router connecting this network to another network, these LAN addresses only exist on the local area network. They can't see LAN addresses on the other network. It's a really important point to remember. So these MAC addresses, they're administered by IEEE, the Institute for Electrical and Electronic Engineers. And as a manufacturer, you're buying some portion of the MAC address space. You're buying a particular identifier for the uppermost 24 bits, and then the lower ones you can assign as you stamp out new network cards. And they act kind of like a social security number. It uniquely identifies every network card, and it identifies it uniquely on its LAN address on the local area network. Okay, and so it's flat. It's not hierarchical like IP. You don't talk about subMACs or subnets. It's a flat address that uniquely identifies you to everyone on the network. And so this allows you to move your LAN card, your Ethernet card, from one network to the next. And it's uniquely identified regardless of where you go. And IP, these IP addresses, they're hierarchical, meaning that you have this notion of subnets. And so while you can move the subnet, you still have to advertise with your router using BGP, eBGP messages that it's managing that block of addresses, but you just can't arbitrarily move a block of IP addresses. Okay, they're hierarchical. So the number value is associated with a subnet, and that subnet is carved out of a larger network, which is carved out of a larger network. They're not completely portable. Okay, so how do you determine a MAC address? Now, of course, certainly you can ascertain what the IP address is. We talked about that with DHCP. And each host that joins the network, it gets an IP address, and it knows its own MAC address. But if you want to send something to a machine on the same shared network, local area, on the same shared medium, you have to know what its MAC address is. But you don't know what those MAC addresses are because they plug in, and you don't know them. You only know your own MAC address, and you know your IP address. You can certainly do a DNS lookup and find out the IP address of another host. But you can't physically send that frame across the network. So this host can't send its frame to any other host on the network unless it knows the MAC address of that other machine. Now, because it knows what the IP address is, it can get that through DNS. It can also get the IP address of the default gateway, the router, first hop router. But it can get all of that through DHCP as well as through DNS lookup, get the IP addresses of other hosts. Okay, great. But it doesn't know the MAC addresses of the other hosts on the same network. How does this happen? Well, there's something called Address Resolution Protocol, or ARP. And ARP populates a table called the ARP table, and this table provides a mapping for each IP address and the associated MAC address. So for example, in this host on the left, let's call that host A, it knows its IP address and its MAC address. It doesn't know the MAC addresses of the other hosts, but it knows the IP addresses of the other hosts. It can look that up through DNS. So then what it does, it says, okay, well, I'm in host A. I'm going to build an ARP table. And how I'm going to build an ARP table is by broadcast, and we'll look at that in a moment. And it's going to store the IP address and the associated MAC address of all the other hosts on the network. So one example of the ARP table on host A, one of those entries would be 137.196.7.78, and it's kind of hard to see that. I apologize. And then the MAC address would be 1A, associated MAC address, 2F, BB, 7609AD. So then, if host A wanted to send a frame to host, call that host B, all host A would say, okay, let me do a DNS lookup of the address for host B. It gets its IP address through DNS lookup, and it consults its ARP table and says, okay, well, what is the MAC address for 137.196.7.78? Looks up in its ARP table, it finds that entry, it says, aha, it's MAC address 1A2FBB7609AD. And then it constructs its frame, and it stamps it with that MAC address, and it sends it across the LAN, and host B picks that up and gets the frame and delivers the datagram to the network layer above. And so this ARP table entry has an IP address, it has the MAC address, and also has this time to live field, so it's leased. And so after a certain amount, this thing gets stale, and then it has to reacquire all of these IP address to MAC address mapping entries in its ARP table. And this is done via broadcast doing an ARP discovery. Okay? All right. So what happens? So let's say A wants to send a datagram to B, and B's MAC address is not known to A. It's not in A's ARP table. And so A then knows the broadcast MAC address. That special MAC address is all one, so it's FF, 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 FF. And whenever you send to that particular destination MAC address, it gets broadcasted to every single node on your local area network. So A does this broadcast, and it says, hey, who here knows the MAC address for B's IP address? And so because it's broadcast, B gets that request, and B says, hey, wait a minute, that IP address belongs to me. And it sends back a response directly to A. How does it know to send back a response directly to A? Because the source MAC address for this broadcast is going to be A's MAC address. So it has the MAC address for A is broadcast everywhere in the network. So let's say you have machine A here, machine B, node C, and let's say you have node D. So then A is going to broadcast its MAC address in the question, who has the IP of B, and that gets sent to everybody. So everybody gets a copy of that. So B gets a copy, MAC address A is asking who has the IP of B. Everyone gets that message. C gets it, D gets it, because it's sent to the broadcast MAC address from A on the link layer. So then B sees that request, gets it because it's broadcast, and it says, oh, wait a minute, I know the MAC address for B's IP. So then B sends back a response to A directly because B knows the source of this message. It's the MAC address for A. So then B sends back a message and says to A, here is the MAC address for B, and that's associated with the IP address for B. And B knows what its own MAC address is for its network card. So then in that, when A gets back that response, it fills in that table entry that says for the IP address for B, it's going to use the MAC address for B. So now A can input the MAC address in a frame, send it on the shared medium, and B is going to get it. Okay. So A broadcasts an ARP query packet containing B's IP address. It sends it to the broadcast MAC address. All nodes on the local area network on the shared medium receive this. B gets it and then replies to A with its MAC address. And A uses this response from B to populate its ARP table. Okay. And so A caches or saves its IP to MAC address pair in its ARP table. And at some point, the TTL expires and it becomes stale, and then A sends a new ARP request because perhaps B has changed, meaning that somebody uses the same IP address, maybe through DHCP, and now the associated MAC address has changed. ARP is a so-called plug-and-play algorithm, meaning that each node, like node A, will continually send these ARP broadcasts, and it will populate or add entries to its ARP table. There's its ARP table as a result of these continuous broadcast requests. Okay, and sometimes it's called an ARP cache. Other times you read in the literature, it's called an ARP table. Okay, so let's take a look at how this might happen if you want to send a datagram between two nodes, A, the source, and B, the destination. And this time, they have to go across network. So they're going to store and forward that datagram using this router. Now, the router shares two interfaces, one with the same subnet on which A exists, and the other on the subnet on which B exists. And so here you'll notice that the router has an interface on the 111.111.111 network, and the router also has another interface that's on its output port that it shares on the other subnet, which is the 222.222.222 network. And so R, well, it has two MAC addresses. It has the MAC address for the interface it shares on the left-hand subnet, and it has the MAC address, this is the MAC address that it shares on the right-hand subnet. Okay, so now let's focus on the addressing that happens. Let's say A knows B's IP address. You do a DNS lookup, it does that iterative or recursive query, and it knows the destination address. So A also knows the IP address of the first hop router. That's the default gateway, and that's this interface for our router here, right? And so this IP address is going to be the default gateway, or the first hop router that A acquires an IP address for when it engaged in DHCP, Dynamic Host Configuration Protocol. And so A knows the IP address of the first hop router, and A also knows R's MAC address. How does it know R's MAC address? Because of ARP. Because of ARP, A will populate its table with the IP address of the router R and also the MAC address for the router R for that LAN. Now you notice here the ARP table for node A, it does not have a mapping for B's IP address. It only has the mapping for IP address to MAC address mappings associated with nodes on the same network. Sometimes this is called in broadcast radius, meaning you're on the same shared medium, right? So this broadcast does not go over the router. A's ARP table has no concept of B's IP address. A knows B's IP address because of DNS lookup, right? That's how it knows the IP address for B. So what happens here? A knows all this information. It has all the IP address to MAC address mappings for its local area network. It knows the IP address of the destination, B, because of DNS. It also knows because of DHCP, it knows the IP address of router R. So A has everything it needs to get that frame first on its local network to the interface that it shares on its local network as router R, and then that frame arrives at router R on that interface it shares with the same network as A, and the datagram inside is delivered to the network layer above. That network layer above then takes the IP address for B, and it checks its forwarding table or flow table, depending on whether it's SDN or traditional routing, and it switches it across to this output port. And then router R, its ARP table has an ARP table associated with the output port also has an ARP table associated with the input port. So the ARP table for router R through ARP, it knows what the MAC address is for B, and it knows what the IP address is for B, and it gets this destination IP address when it forwards it out this port. It says, okay, where is it destined? It's destined for that IP address associated with B. So it knows the IP address for B. So then when it sends out that frame, it goes down from the network layer to the link layer on the router for this other interface it shares with the network on the right-hand side that it shares with B. It then says, okay, well, the destination address is B. I need to fill in the MAC address. What is the MAC address that's associated? Well, from its ARP table, it knows for the IP address for B, you're going to associate that with the MAC address for B. So it knows the destination MAC address. So it sends that frame out, and it can get that frame to B. So in each network, you're using ARP to get that frame from one node on the network to the other node on the network, the other link layer. And then once you get to the router, you're using the IP address in layer 3 to determine the output port. And once you get to the output port, you're then using the ARP table to get it from this particular interface to the MAC address or link layer of that destination machine on the same network. So ARP corresponds to a conversation between nodes on the same network, between link layers associated with nodes on the same network. Okay, so let's take a look at this. We have the source IP address and the destination IP address. This datagram is encapsulated into a frame. The source MAC address is the source MAC address for A. The destination MAC address is going to be the destination MAC address for the interface on that left-hand network associated with the router. So it sends that to the router. That frame goes across the physical medium, comes up to the link layer. It extracts that datagram, sends it to the network layer. The router then switches it across, sends it to the output port. It has the destination IP address, consults its ARP table. It knows when it sends it down into the link layer what that destination MAC address should be, puts that frame on the physical layer, and that frame makes its way across to the link layer of B, and it extracts that datagram, sends it to the network layer above, and you get that as a video frame or an HTTP response and so forth. Okay, so R forwards the datagram with IP of source A and destination B. It creates a link layer frame with B's MAC address as the destination address, and that frame contains the A to B IP datagram. And so there's this interchange as it pertains to the MAC addresses that gets that datagram between nodes on the same network, but the IP address gets that datagram from one port of the router to the other port of the router, and that other port of the router is another interface that's on a different network. And that other interface on a different network, it has acquired through its ARP table all of the IP address to MAC address mappings. So that's how this all kind of comes together. All right. So let's take a look at Ethernet. Ethernet is the dominant wired local area network technology. It can be single chip in all sorts of different speeds, the most widely used local area network technology. And it's cheap. And because it's so cheap, it's ubiquitous. And it's continually kept up with increasing the speed by changing the signaling protocol. And you can have 10 gigabit Ethernet. And in fact, right now you can get 1 gigabit to a home, to a residence. That was unheard of even just 15, 20 years ago. And so this is the original sketch of Ethernet. Bob Metcalfe, the creator of Ethernet, one of the creators, well, sort of credited with creating it, for how Ethernet works. It was a shared medium called the ether. So there were, in the beginning, you had different so-called topologies or arrangements of how the shared medium was arranged for this Ethernet. And the bus-based configuration was very popular into the mid-90s. In this, all nodes were physically connected through their interface and kind of tapped into the same conductor. This meant you had so-called collisions, meaning that two communicating nodes, or more than two, could start to talk at the same time. So let's say you had A, let's say you had B, A was trying to send signal information that was intended for B. Now, as a conductor, this signal information is going to make it to every single node on the network because it's a physical conductor. Now, all of a sudden, if C at the same time tried to send signal information to D, well, that would mean there would be two instances of signals from A to B and from C to D at the same time, and you're going to get interference. That's called a collision. They're trying to talk over the shared medium at the same time. It's like two people trying to talk at the same time. You're going to get interference. And so nobody's going to get their message clearly. And so this bus-based approach requires you to arbitrate to make sure that you can coordinate that only two communicating endpoints at a time can use this shared medium. But it was very popular. It resulted in collisions, but there were methods to arbitrate and make sure that only two endpoints were sending and receiving at the same time, at a given time. So then you have this thing called the star topologies, the hub and spoke. This is what a star looks like. And initially, the star started out as just a bunch of connectors that extend like spokes from a single conductor. And what was introduced is this device called a switch. And this device takes link layer frames, and depending on the source and destination MAC address, it can forward them to the destination's spoke, if you will. And in doing so, it avoids collisions. And it can do this in parallel. So host A can send to B, and at the same time, C can send to D. As long as the source and the destination are different, you can have parallel conversations without collisions. And so this is why so-called switched Ethernet is much, much faster, because when you have collisions, you're using some of the bandwidth available on the medium to coordinate between the nodes so that you don't get these collisions, or so they react appropriately to collisions. Now, in switched Ethernet, it introduces this device called a switch, which is a kind of pass-through based on the MAC address as the source MAC address and the destination MAC address. And we'll talk about how switches work. And so this star topology, the star arrangement, the hub and spoke arrangement of nodes on the same network is what prevails and persists even today. Okay. And so this is the Ethernet frame structure. And the payload area, this is the datagram from the network layer. Datagram. And the other header information that's meaningful to the link layer frame is a number of things. You have a preamble, and this preamble is just a marching pattern, alternating pattern of 1 0 1 0. And this is what the Ethernet card uses to synchronize its clock so that it performs certain actions at a certain pace. And so that's what the preamble looks like. It's a bunch of bytes, 7 bytes to be exact, in a particular pattern that the Ethernet cards use to synchronize. It has the destination MAC address. It has the source MAC address. It has a type field, and that sets the type of Ethernet protocol used. It has the payload, which is the datagram from the network layer above. And then it has this thing called a CRC. It's called a cyclic redundancy check. It's a way of doing error detection and correction. It's kind of like doing checksums, but it does a running checksum over a sequence. So the link layer is doing its own error correction and detection, only it does a little bit differently over sequences. Okay, and so the reason why you have a preamble is so that you can synchronize between the sender and receiver, because the sender and receiver both need to know, here's the sender, here's the receiver. If it has a certain number of bits, bit 0, 1, 2, 3, 4, it has to know, okay, now send me the first bit, now send me the second bit, now send me the third bit, and so forth. And so you need to synchronize. And if you're expecting a certain pattern, 1, 0, 1, 0, 1, 0, 1, 0, you can say, okay, well, let me set my clock so that it's consistent with these patterns that are coming in, so that I can know that I'm getting the first bit or the second bit or the third bit from the sender. And so that's the purpose of this preamble. Now, these addresses, these are MAC addresses, and we talked about MAC addresses before as being 6 bytes long, where each byte is 8 bits, and we have 2 hex digits per byte. And so we have 3 bytes representing the vendor ID, and 3 bytes representing the Ethernet card from that vendor. And these are unique. They're the source and destination MAC address. Now, the type field indicates the higher level protocol. For typically, it's Internet Protocol IP, but there are other possibilities like AppleTalk, which is Apple's proprietary network layer to use to talk between different Apple devices. And that is one of the type field possibilities, but usually it's IP for the most part. And of course, we talked about cyclic redundancy check. It's used for error detection and responding to those errors. So it's kind of like a checksum, but it's a little bit different. It uses running streams of bytes instead of just adding and carrying in one's complement. Okay. So Ethernet is unreliable. It's connectionless. There's no handshaking between the sending and receiving NIC, network interface card, at the link layer. Now, it doesn't impact the resend by TCP. So remember, TCP, when you make this RDT call, you make the call to the unreliable channel below. Well, Ethernet is part of that unreliable channel below. And so while Ethernet itself, the link layer, is unreliable, if there's corruption, well, ultimately TCP will cause a retransmit. Ethernet has a media access control protocol, this arbitrating between two or more nodes that are colliding, trying to use a shared medium. It's called CSMACD, Carrier Sense Multiple Access Collision Detect. And so what this carrier is, it's a frequency of some signal, a frequency. Carrier sense is detecting that signal at a certain frequency, multiple access, how many times or how many different people are contributing this signal energy. So that's the carrier sense, sensing the carrier, multiple access. Collision detect are more than one carrier wave being sent on this shared medium at a time. And so this binary backoff is it randomly selects a binary number, and it uses that binary number as a timer to say, okay, I'm going to randomly select some amount of time for which I'll go to sleep and then come back. And so because it's uniformly at random, very rarely or no two nodes will select the same binary number for which to go to sleep and come back. So therefore, you'll come back at a different time from someone else who's trying to access the channel at the same time. So that's how this sharing of the shared medium is done. Okay. So there are many different types of Ethernet standards, and these Ethernet standards have different names based on the speed. And so you have fiber, and these fiber standards for your cabling has different names like 100 base SX, 100 base FX. And then for the copper twisted wire, you have different names like 100 base T, 10 base T. And so when you buy this Ethernet cable, you pay different money for different cablings because they support different speeds. The engineering is a little bit better, the shielding is a little bit better. It can support higher bandwidth transmission rates. And so you have different speeds. You have 2 megabit, 10 megabit. 100 megabit is getting to be old. Category Cat 6 cabling, Cat 5 cabling, you can get 1 gigabit per second. 10 gigabit is coming online, being more common, local area network, and you have different physical layers. And so for these physical layers, you have different standards, and you're going to pay different money depending on what standard is supported for the bandwidth, whether it's fiber optic strand or it's twisted pair network cable. And so the MAC address and the protocol for the link layer access and the framing and the media access, that all is implemented in your link layer, but the physical layer is the standard for the cabling that you use. Okay, and so we're going to end there. This is a good stopping point, and we'll pick back up next time with switches and VLANs. We'll pick back up on Tuesday. So I'll see you all